welcome to Modern Physics. We're on lesson 5 and we're going to talk about radioactivity 1. So in lesson 5 part 1, we're going to look at the 3 types of radiation. They're called alpha, beta and gamma. I'll tell you the story of where that came about. So go to your notes on that section. Lesson 5 part 1, the 3 types of radiation. You're going to draw a cloud or bubble chamber in the space provided. So let's get to telling the story. The story starts in 1896. We have this famous scientist working in Paris called Henri Becquerel. And Becquerel accidentally made this discovery. Becquerel was playing around with some uranium salts. They contain large amounts of uranium. And when he was leaving the office one weekend, he took some uranium and he wrapped it in photographic paper. So here's the photographic paper. And here is my uranium. The chemical symbol for uranium is U. So he wrapped that and he put that into a darkened drawer. He went away for the weekend. Then he came back on the Monday and he opened up the photographic paper and he saw all over the photographic paper, he saw these marks or etchings. The photographic paper is how we used to take pictures before our mobile phones and so on. So basically, when the light hit the photographic paper, it would form an image and you would develop the image then later on. So he was saying to himself, did light actually get into the drawer to cause that to happen? So he did the experiment again, this time more carefully. So he wrapped the uranium in the photographic paper and he made sure that absolutely no light could get at the photographic paper. And once again, when he opened it up after a day or two, he saw these markings. So these markings, he said, they must be coming from the uranium. That uranium is spewing out some kind of invisible radiation. That invisible radiation he called radioactivity. At this stage, they had absolutely no idea what that stuff getting spewed out from the uranium was. That's the first part of the story. The next part of the story was to take the uranium and try to analyze and find out what radiation, what invisible stuff was getting fired out from the uranium. So here's the next part of the story. I want you to draw this with me in your notes. The next part of the story was we take something called a cloud or a bubble chamber. This is something that contains some kind of vapor. The vapor could be something like liquid hydrogen. So liquid hydrogen at room temperature will rapidly turn into a gas. So there's a gas in there, a clear gas inside that chamber. Now we're going to put our uranium in there. And we're going to put our uranium inside a piece of lead. Why lead? Well, lead is a very, very heavy metal. It's a very dense metal. And it's very hard for the radiation to pass through that. So we take our piece of lead and we cut a little channel through that lead. And in there, I drop in the uranium. So the uranium is in there. We call that sometimes the source of the radiation. So this here is a piece of lead. Why did I do it that way? Well, because, look, the radiation is going to get spewed out in every direction possible. Anything that goes left or right or down just gets absorbed by the lead. So I end up getting a nice narrow beam or channel of radiation coming up through there. They also decided to do another thing. They decided to put in 2 metal plates into the bubble chamber. They put one metal plate up here and another metal plate here. These are called electrodes, and they connected them to a battery. This side here was the negative battery, say, and this side here was the positive battery. Plates with those charges on them are called cathode, is the negative plate, and the anode is the positive plate. Now, these little invisible bullets that are getting spewed out from the source, We can't see them. But when they go flying through the vapor or the liquid hydrogen, what they do is they ionize it. They knock electrons out. And when that happens, that vapor produces a cloudy appearance, just like clouds that you see in the sky. So when you ionize it, it'll turn the vapor into a cloud. And as those little bullets that get spewed out from the source produce these clouds, you can see there are cloud trails. So when they had a look at the trails that were formed, the cloudy trails, they could see that one set of trails went straight up, like that. One set of trails got drawn in that direction towards the cathode, and another set of trails got attracted towards the anode. So they saw that there were three types of particles getting spewed out. I mean, the particles that went straight up, they were unaffected by the electrodes. So they must have been neutral, no charge. The ones that got attracted towards the cathode, they must be positive to be attracted by the negative cathode. And these particles here, they were attracted by the anode. They must have been negative. So you had negative particles, positive particles, and particles with zero charge. Again, they had no idea what they were. So they decided to call them the first three letters of the alphabet, A, B, C. Well, actually, the first three letters of the Greek alphabet. So they call these ones alpha particles. They call these ones here beta particles. And they call these ones here gamma particles. So they're the three types of radiation. They're called alpha, beta, and gamma. So be able to say them. They're the alphas. Now, they're made up names, but we still use them when we talk about nuclear radiation today. These are your betas, and these are your gammas. So that's the second part of the story. First part of the story, Becquerel discovered something mysterious was getting spewed out of the uranium. Second part of the story was we put them into the bubble chamber and we separated them into three types of particles called alpha, beta, and gamma. And the next part of the story is let's actually siphon off those alphas, siphon off those betas, siphon off those gammas, and let the chemists do their work to try and discover exactly what they are. So the next part of the story is to find out exactly what alphas, betas, and gammas were. So as I said, the chemists got to work to try and find out what they were. So we need to know the properties of the various radiations. So let me go through these on the board. Starting off with alphas. Well, what can we say about alphas? You can see they are deflected in electric fields, also magnetic fields. And you can see the direction of deflection. They're being attracted towards the negative, the cathode. That means they must be positive. The first thing I can say about alphas is that they are positive, positively charged particles. Anyway, the chemists got to work and they found out by doing lots and lots of experiments, they discovered that alphas were equal to helium nuclei. Well, if you go to the periodic table and you write down the numbers for helium, helium He, the numbers are 2, 4. That means the number of particles in a helium nucleus, it's got 2 protons. Take them away, 2 neutrons. It's got 4 nucleons altogether. That's a helium nucleus. So if I was to draw a very simple picture of it, here's my 4 nucleons. It's got protons, 2 protons, 2 neutrons. And you know the charge of each proton is +1. Neutrons are neutral. And therefore the charge of an alpha particle or helium nucleus is +2. 2 protons giving me +2. So that's what they discovered alpha particles were. They would ask themselves later on, how come helium nuclei are getting kicked out of nuclei? But that's for the story later on. So I'm kind of telling the story as it was discovered. So they just saw that alphas were helium nuclei. Later on, they'd ask the questions as to why helium nuclei get kicked out. Now, these helium nuclei, they're actually quite big. So they are very high ionizers. They have a high ionizing ability. Now, what that means is they're going to crash into, let's say, air molecules. And every time they crash into an air molecule, they'll kick an electron out. And now you've got an air molecule that's charged or ionized. So if I take my alpha particle, which I'll draw like that, and here's all these air molecules all over the place, that alpha particle keeps on crashing into them. And every time it crashes into them, it'll kick out or absorb an electron. So these are these little electrons. And those electrons get knocked out when the alpha crashes into them. And therefore, you're going to be left behind with a positive charge. So you are ionizing the material through which you travel. So they've got very high ionizing ability simply because alphas are so big. They're going to keep on crashing into the air molecules. Smaller particles are able to sneak their way through without causing lots of ionization. Now, associated with having a high ionizing ability means it doesn't get very far. If you keep on crashing into things, you're going to slow down rapidly. So therefore, you have a very low penetration power. So the two things are linked. The high ionizing ability means you're crashing into things all the time, knocking out electrons. And that means the particle, the alpha particle, is losing energy rapidly. So it's not going to get very far. It's got a very low penetration power. The range, which you should know, the range of an alpha particle is approximately 6 centimeters in air. That's not very far. So if you've got a radioactive source that's kicking out alpha particles, they go about 6 centimeters in air and they lose all their energy and they kind of drop dead. So they don't sound very dangerous because if they only go 6 centimeters in air, they're hardly going to be penetrating your skin. But they can be different. They can be dangerous in another session, which we'll talk about later. So the last property, and you've got a list of 5 properties in your notes. The last property is when they come out of the nucleus, they're traveling all about the same speed, and the speed of emission of these particles is about 10 to the power of 7 meters per second. So they're coming out quite fast, but they don't go very far because of their high ionizing ability, and therefore they have a low penetration power, their range being about 6 centimeters in air. Okay, so I need to know those properties quite well. So learn that list that's provided in your notes. The next particle we look at are beta particles. So the chemists got to work on the beta particles and they came up with their properties, which you need to know. So let's go through the beta particle. Well, the first thing we know is these are the betas. They're deflected in electric fields, and all charged particles are also deflected in magnetic fields. And you can see the direction of deflection shows they must be negative because they're being attracted towards the positive anode. The positive electrode is the anode. So therefore I can say they are negatively charged. So as I said, the chemists got to work. They did all kinds of experiments to find out what they were. And to their amazement, they discovered these betas were high-speed electrons, which kind of perplexed them. Electrons we think of as orbiting around the nucleus, and now we're talking about electrons coming from inside the nucleus. So again, I'm telling the story in sequential order. So later on, they'd get more understanding of why electrons were coming from inside the nucleus. The electron we call E, little e, and the numbers on the electron are -1, 0. So what can I say about my little electrons? Well, they're very small compared to the alpha. You know that one proton or one neutron, a nucleon, is about 2,000 times bigger than an electron? If you've got 4 nucleons that you have in an alpha particle, that's 4 times 2,000, which is 8,000. So alphas are about 8,000 times bigger than your electron. So you can imagine then, when the electron goes flying through the air, here's my air molecules, they're very, very small, so they can sneak their way through. So they're not going to interact with the much bulkier, they're not going to interact with the air molecules like the much bulkier alpha particles. So they will occasionally crash in and they will knock an electron out, which is called ionization. But we say they have a lower ionizing ability to alphas. So a lower ionizing ability because they're not going to crash into the air molecules as often because they're much smaller. Now, if you have a lower ionizing ability, that means you can go further without getting slowed down. That means you have a higher penetration power. How far do electrons go in air on average? That's their range. Their range is about approximately 500 centimeters in air compared to alphas, which only go 6 centimeters. So about 500 centimeters in air. They're actually more dangerous because they're more penetrating. So they land in your skin, they can dig in deeper, go into your nuclei and so on. So they are more dangerous. They're emitted from the nucleus with a whole range of speeds, up to a speed of about 2.7 by 10 to the power 7 meters per second. So now, what do we know? Betas, they're negatively charged. They're actually high-speed electrons. They have a lower ionizing ability because they're so small. They can creep through the air molecules, and therefore they go further. Their range is about 500 centimeters in air. So learn those properties very well. The final piece of radiation of the 3 types is gamma radiation. So they were analyzed. And what did they discover about the gammas? Well, if you look at the cloud chamber, the gammas went straight up. They weren't deflected by the electric charges on the plates. So they're not deflected in electric or magnetic fields. And therefore, we can say gammas are uncharged. What exactly are they? Well, they did experiments and they found they weren't particles at all. They were photons, photons of light, but very, very high energy light. You're talking about having this enormous frequency. Much higher than X-rays. And X-rays are dangerous. So you can imagine gammas, they're probably the most dangerous types of electromagnetic radiation. They have a very, very small wavelength and they have a very, very high frequency. That means they have a huge amount of energy. Because remember the formula for energy? The energy in a photon is h times f, where h is Planck's constant. So if the frequency is extraordinarily high, that means they have a huge amount of energy, and that means they're very dangerous. They can creep through air with hardly any interaction. So they have a very, very low ionizing ability. So they only occasionally encounter an air molecule, and therefore they will ionize it. So they have a very, very low ionizing ability, and therefore they have a very high penetration power. They will go forever and ever. Air won't stop them. You'll probably need lead to stop them. The range is about 1 centimeter of lead. Lead is a very, very dense metal, and they're still able to get through about 1 centimeter of lead before getting slowed down, before losing energy. So that's your gamma radiation. They're not particles at all. They're high energy photons. They travel at the speed of light, of course, because they're photons. They travel at 3 by 10 to the power of 8 meters per second, just like all electromagnetic radiation. So just to summarize, we have three types of radiation. We call them alpha, beta, and gamma. First three letters of the Greek alphabet. But we've actually retained those names. We analyze what alphas are. Alphas are actually helium nuclei, He24. Betas are high-speed electrons. And gammas are high-energy electromagnetic radiation that travels at the speed of light. Their properties, they're positively charged, they're negatively charged, they're neutral. These are very big, they have a high ionizing ability, and therefore a low penetration power. Their range is about 1 centimeter in air. These are much, much smaller, therefore they have a lower ionizing ability because they don't crash into the air molecules too often. They go further, their range is about 500 centimeters in air. And gammas, these aren't particles at all. They can creep through the air with hardly interacting with it. So they have a very, very low ionizing ability. That means they go very far. Air won't stop them. You probably need 1 centimeter of lead to actually stop them.